Welcome to the Deep Dive, the place where we take the latest research, distill the most explosive insights, and give you that competitive edge in knowledge.
Today, we're really challenging the fundamental idea of what a robot is. If you're picturing C-3PO, some kind of android
Right.
that's looking backwards.
Right, not the Hollywood version.
Exactly. The real AI-Robotics Frontier isn't about building humanoids. It's about systems that are, well, small, soft, deeply integrated. They're designed not to replace us, but actually improve life.
Improve life how?
Think inside the body, on our bodies, and just seamlessly in our homes.
Okay, that's a huge idea. Let's unpack it.
Yeah.
We've dug into the work of two really powerful research groups at Stanford School of Engineering. On one side, you've got the Assistive Robotics and Manipulation Lab, ARM. They're the experts in hard control manipulation.
Right, the traditional robotics, in a sense.
And on the other, the Soft Intelligent Materials Lab. Engineers of the future, maybe?
You could say that.
So our mission for you today is to connect these seemingly opposite fields, the rigid and the soft. We want to understand the immediate societal needs that are driving robotics development right now, globally.
And that mission, looking at the needs, is probably the best predictive indicator you have. If you want to know what robots will actually be doing in 10 years, don't look at sci-fi. Look at society's biggest, most persistent, unmet needs right now.
Okay, so what are those needs? What's screaming out for robotic solutions today?
Well, the research points to about 4 key areas. The first one is maybe the most human, the world's rapidly aging population.
Makes sense.
People want to stay in their homes longer, right? But they need help with these tiny, dexterous tasks. Opening medicine bottles, maybe threading a needle.
Things that get harder with age.
Exactly. Things that become physically painful or just impossible. Robots designed specifically for that kind of dexterity could fill a really critical gap.
That definitely has a huge quality of life concern. The second area you mentioned, manufacturing, that sounds like a different kind of challenge. More economic.
Absolutely. Think about global supply chains, the push for onshoring, bringing production back home.
Right.
We know that, for example, just assembling an affordable pen in the United States, it's basically economically impossible right now.
Why? Labor costs.
Labor costs tied to complex assembly. So robotics that can handle the nuance of fine assembly, not just brute force factory work, are essential to solving that cost problem.
So this isn't just about faster conveyor belts then. It's about getting the complexity of a human hand, but consistently, affordably, to bring that high dexterity assembly back.
Precisely. The third area is challenging environments. Think agriculture harvesting, planting, conditions that are just too harsh or repetitive for sustainable human labor.
Right.
And finally, the fourth area, highly integrated wearable systems. Things like advanced prosthetics.
Where the robot is basically part of the user.
Exactly. And there, the system has to get really good at figuring out human intent from minimal cues, to offer genuinely helpful assistance.
That need for precision control, for intent, it brings us right to maybe the biggest barrier, stopping robots from being truly useful in the home. I mean, why don't we all have robots doing the laundry or loading the dishwasher yet?
Yeah, it really comes down to cost justification, and that's tied directly to utility.
Utility meaning, can it actually do enough useful stuff?
Right. We, as humans, take complex manipulation totally for granted. Until a robot can reliably handle the nuanced, dexterous tasks we think are simple, well, it's just not worth the cost of, say, a new car.
And this is where the sources hit on something really surprising. The barrier isn't just sight, it's touch. The primacy of touch.
Yes. There was this fascinating experiment mentioned. An individual was asked to strike a match. Pretty simple task.
Okay.
But when they made their finger numb so they couldn't feel but could still see perfectly well,
What?
It took them 3 to 4 times longer to actually strike the match successfully.
Wow. 3 to 4 times longer. Just from losing touch, even seeing it clearly.
Exactly. It shows that touch isn't just some secondary sense. It's core to our internal control policy. Vision tells us where things are, kind of globally.
But touch tells you.
Touch tells you how the forces are interacting right now, second by second, millisecond by millisecond. It allows for those instant, tiny adjustments. Without it, our dexterity is just crippled.
Okay, so if touch is the key, the absolute key to unlocking dexterity, how do we give robots fingers that can feel the world? This brings us to the ARM lab's work, right? These dense tactile sensors.
Yeah, that's their focus. They're essentially creating these high-resolution digital fingertips. We're talking thousands of pixels of force feedback.
Like a tiny, sensitive camera for touch.
Sort of, yeah. It gives the robot the ability to sort objects based purely on feel. For example, they showed a robot reaching into a bowl of mixed screws and sorting them correctly without using any vision at all, just feeling the thread pitch, the head shape.
That's incredible. And what about that anecdote about practicing gentleness? How does a robot practice being gentle? That sounds very unrobotic.
It's all about the closed-loop system, feedback and error correction. They use the example of picking up a fragile strawberry.
Okay.
The robot picks it up, the sensor registers exactly how much force was used, and crucially, it characterizes the physical damage done to the strawberry.
It can tell if it squished it?
Precisely. It uses that damage data to adjust its grip, its force profile, and then it tries again, hundreds, maybe thousands of times, until it learns the force profile that minimizes damage. It's data-driven learning, focused purely on delicate touch.
And this has to be affordable, right?
Yeah.
You mentioned cost earlier. You can't have million-dollar fingers.
Absolutely critical. The dense tactile sensor they developed costs under $40.
Under $40?
Yeah. And most of that cost is actually the miniature camera inside that measures the deformation of the sensor pad. That low cost point is what makes scalable high-dexterity robotics potentially achievable for consumers, for manufacturing.
Okay, so we've spent time on these hard control systems for manipulating things externally, the strawberry, the screw. But now we need to shift gears, make a conceptual leap from the macro problem of touching an object
to the micro problem.
Right. Navigating the most confined, complex environment you can imagine inside the human body.
And this is where the Soft Intelligent Materials Lab really comes in. Their approach is a complete contrast to the rigid, motor-driven systems of the ARM lab.
Soft materials. Why are they revolutionary?
They offer what's called infinite degrees of freedom.
Infinite degrees of freedom. What does that actually mean in practice?
It means basically every single point in the material of the soft body can deform. A rigid robot arm is limited by its joints, right?
Sure.
But a soft system can achieve multimodal deformation. It can bend, twist, fold, conform to its environment in really complex ways. They get inspiration directly from biology.
Like what?
Think of an octopus arm. The agility there is incredible. Or an earthworm burrowing, or an elephant's trunk. Nature figured this out long ago.
And that allows for extreme miniaturization too, doesn't it? Especially if the material itself responds to external energy.
Precisely. They use these stimuli-responsive materials. They react to things like temperature or, really importantly, magnetic fields.
Why magnetic fields?
Because it lets the researchers separate the bulky control unit, the magnet source, the power source, from the tiny robot itself. This leads to, well, unprecedented miniaturization.
And that miniaturization is critical for things like stroke treatment. You mentioned clot-related diseases cause over 25% of global deaths. What's the issue with current stroke treatments?
The standard is mechanical thrombectomy. They use a long catheter to basically go in and fish out the blood clot.
Sounds straightforward.
But the brain's vasculature, the blood vessels, are incredibly tortuous, lots of sharp, tight turns. Rigid catheters often just can't navigate to the clot site. The procedure fails.
Okay, I see the problem. So the soft lab solution is the millispinner. What does this tiny 1 millimeter device do?
Right. The millispinner is coupled to an aspiration catheter. It has this tiny spinning component. But it does something really clever. It doesn't just try to cut the clot up.
Why not? Risk of pieces breaking off.
Exactly. Fragmentation is dangerous. Instead, the millispinner works by fundamentally changing the clot's structure.
How?
Think of the clot as this meshwork called the fibrin network. It's like a loose, wet sponge full of red blood cells.
Okay.
The millispinner spins and actually contracts that fibrin network. It densifies it, effectively squeezing out the red blood cells.
So it shrinks the sponge, makes it smaller and denser.
Exactly. They achieve over 95% volume reduction. This makes the remaining, much denser clot far smaller and much easier and safer to just pull out through the catheter.
Over 95% volume reduction. That's a massive improvement in reliability. Yeah. And the ultimate goal is no tether at all.
Yeah. The next frontier is the magnetic millispinner. This tiny component, controlled externally by magnets, could potentially swim super fast right through the blood vessel.
Yeah.
And the idea is it could digest the clot in situ right there without any mechanical fragmentation. That's the ultimate safety goal.
This is incredible engineering, incredible biology, but the success of both that tiny surgical robot and the gentle strawberry grabber hinges on control. So let's talk about the brains behind it all, the AI synergy.
Yeah, we hear AI thrown around constantly, but in robotics control, it's actually quite simple at its core. AI is just looking for patterns.
Input to predictable output.
Right. It takes an input, predicts a repeatable output. You typically use it when you don't have a nice, clean mathematical formula and an analytical representation to describe what needs to happen.
So when you can use a formula, you do.
Yeah.
Like the ARM lab solving singular poses in robot arms. Wait, what's a singular pose? Is that like when the arm gets stuck?
That's a great way to think about it. Imagine you stretch your own arm straight up. Mathematically, for the robot, multiple movement solutions collapse into one point. It can lock up or get really unstable. The researchers figured out how to solve this analytically in real time, which is crucial for making robot arms easier to control, smoother, and absolutely essential for the kind of precise, reliable movements needed in surgery.
So that analytical precision handles the knowns. And that clears the way for the data-driven AI when things get too complex for clean math. Like training robots by watching human surgeons.
Exactly. You collect massive amounts of data on how a top human surgeon handles a difficult case, maybe a really complex clot type, or navigating super tortuous anatomy. The robot then learns to replicate those decisions when it sees similar input data from its sensors. It essentially becomes a learned surgical co-pilot.
And this brings us to that moment where the two labs really intersect.
Yeah.
The closed-loop collaboration, the big robotic arm, the hard control system.
It's providing the external magnetic field
to guide the tiny magnetic millispinner, the soft material robot.
That entire control loop is, well, it's the technical Everest here. You have to couple the robot arm's precision with real-time X-ray imaging. It's called fluoroguidance.
And the fluoroguidance only gives you a 2D image, right? A flat picture.
Correct. And that's the core challenge. Mapping that flat 2D image onto the complex, unique 3D brain vasculature of every single patient.
Because no two brains are identical.
Not at all. The control system has to interpret that flat image and accurately navigate this tiny spinner through a 3D maze in real time inside a flowing dynamic environment. It's incredibly hard.
But if they crack it, that level of automation, combining surgical precision with soft robot navigation, the implications are staggering. The source material mentioned Stanford only has 4 neurointerventional radiologists.
Yeah, imagine. This technology could dramatically reduce the reliance on those few highly specialized, highly trained doctors.
It democratizes access, then.
Absolutely. By automating the really difficult navigation part, this tech could potentially bring immediate, reliable stroke care to rural hospitals, to places that simply don't have that specialized expertise right now.
This raises a really powerful question about shared autonomy. If we can automate guiding a device through the brain, what level of control do we, the human users, actually need for something like, say, an advanced prosthetic?
That's the prosthetic challenge we touched on earlier. We know high-res touch is key. 4 different modalities were mentioned: normal force, 2 kinds of sliding friction, and torsion or twisting.
Okay, complex data. How do you get that feeling from a prosthetic finger back to the wearer?
It's extremely difficult. The nerve density on most of our body, like the forearm where a prosthetic attaches, is pretty sparse compared to our hands or face.
Right.
You can't just put a simple vibration motor there and expect the user to truly feel the object in detail.
So what are the alternatives?
Researchers are exploring different interfaces. One idea was using tiny vibration motors placed on the cheek. It's a highly sensitive area to convey what the prosthetic finger is feeling.
Interesting. Using a different body part.
Or using augmented reality. The robot's sensors process the complex force profile, and the human wears an AR headset that displays some kind of visual representation of that force. They then learn to map that visual cue back to a sense of touch, cognitively.
So you're kind of bypassing the direct nerve connection, using sight or another sense to build a mental map of the feeling.
Exactly. And this leads to this maybe counterintuitive idea about shared autonomy. Perhaps the human doesn't need to feel every single tiny detail of a complex task, like untying a really small knot.
The robot handles the fiddly bits.
Maybe. The robot, using its dense sensors and advanced training, handles the physical complexity itself. The human just needs to provide the basic, high-level intent. I want you to untie this knot.
Before we wrap up, let's just touch back on those soft, stimuli-responsive materials. Beyond medicine, where else might they be useful?
Well, because these materials are designed to passively deform and conform, they mentioned origami-like structures. They're potentially perfect for confined, messy environments. Think industrial settings, maybe environmental cleanup, places where a rigid robot would just get stuck or break.
And separating the driving force, like the magnet, from the robot itself.
Means the robot can be incredibly lightweight, simple, robust. It opens up countless applications in areas like manufacturing, inspection, maintenance, things we probably haven't even conceived of yet.
So when we started this deep dive, we challenged that Hollywood idea of the robot. What we've really concluded is that the true frontier is much more subtle, it's smarter, and it's definitely softer.
Yeah, it's a future driven by necessity, where robotics are touch-sensitive, deeply integrated into human care, whether that's surgery or daily living, and they rely on this sophisticated blend of precise analytical control and AI-driven learning from observation.
We heard today that the robot of the future needs to handle these incredibly dexterous tasks, navigating a brain vessel, untying a complex knot, basically using its own built-in sense of touch in its training. All it needs from the human is the basic intent.
Right. Which leaves us with, I think, an important question for you, the listener, to think about. If robots increasingly take over the precise, repeatable physical complexities of the world, what complex non-physical skill will you focus on developing next?